All right, a W200 times 31.3 rolled steel beam is subjected to a couple M of moment, 45 kilonewton meters. Knowing that E is equal to 200 gigapascals and the Poisson's ratio is 0.29, determine A, the radius of curvature. We're not going to need that one. And don't think I know this because I'm super fast at understanding the problem. I just did it earlier. I complicated my life, then realized I didn't need that one for answering part A. So when you see W200 times 31.3, that means you probably want to look at an appendix, right? So go at the end of the book, and I'll tell you in a second what that is for this particular exercise. But how do we find this? Well, we got to think about a beam. Let's just think about a generic beam before pure bending. Okay, once I apply a moment, couple, what's going to happen? Well, it's going to bend, right? So notice that the top part is going to shrink, the bottom is going to expand. So now, let's take this and let's say that there's a center of a circle right here from which this bending applies. And so say that this is my rho. This distance is my rho. And this is my theta. So what am I going to say now? Well, let's say that this is my AB and this is my, A starts from the neutral axis, and then we go to A prime, B prime. So we can say that our deformation, or actually our strain in the y direction, is equal to, or in the I'm not sure if it's in the x or y. Our strain should be in the y direction, is equal to rho plus y, and that's rho plus this little distance, times theta in radians, plus just the radius times theta, divided by original length, rho theta. So the thetas cancel out, and that's going to be a minus, because we're looking at the difference in length between the arc A prime, B prime, and the arc AB. And so what we get out of this is y over rho. Now, remember that if we're in the elastic region, then we can say that sigma x is equal to epsilon E epsilon x. So this is epsilon x, to my knowledge. So we can say sigma x over E is equal to epsilon x. And we can plug that in. So we can say, I don't know why I'm doing everything there. We can move over here. So we can say that sigma x over E equals y over rho. And now that we do that, what happens? Well, we know that sigma x is equal to the integral of let me think. Sorry, I didn't want to do this. I wanted to do I want to say that the moment is equal to the integral of sigma y, distance y, times dA. Right? Because it's a force times y that gives us a moment. And so if we substitute what we said for sigma, then we get basically YE over rho times Y dA. And so we can pull out E over rho because we know that to be constant in the elastic region. So we get Y squared dA. Y squared dA is our moment of inertia. So that's EY over rho. And so now I think we have everything we need. So rho, and if you have the formula on the sheet, then you can just use that. But I wanted to show where it came from. And I just got stuck a little bit on this part. Sorry about that. So now we have 200 times 10 to the 9th newtons per meter squared. And we're going to multiply by I. And the I of the beam, you can find it on the book. So it's going to be I with respect to X, which is our Z in this case. And so hopefully that's what we should get. 31.3. Let me just make sure. Yes, 31.3. And it should be, let me give you the units, times 10 to the 6 millimeters to the 4th. 31, and that goes right here, 31.3 times 10 to the 6 millimeters to the 4th. All of that, we want to divide it by the moment. And the moment that they give us is 45 kilonewtons. So that's 45000 newtons. And so what do we get out of this? So that's going to be 200 times 10 to the 9th times 31.3 times 10 to the 6th divided by 45000. Now remember, this is a millimeters, so we want to convert 1 meter every 1,000 millimeters to the 4th power. So that's going to be times 1 over 1,000 to the 4th power. And we get 139. So we get 139.1 meters. Now you might think, hey, this is large. Well, think about it. The beam is not going to bend a lot. So it's not going to bend like this. It's going to have a curvature that's imperceptible. So the whole, circle is going to be huge, right? So that's how to do it. I think the only thing I'm kind of sketchy on is this idea that this is the epsilon x, because we are saying that that's our y direction. So that's the only thing I'm a little confused about. I hope this was fun for you, and I'll see you next time.